Y'all, welcome. I am so excited about today's lesson. Who knows, maybe a little too excited. But today is the first day where you're really going to start getting a feel for how the tools that you have been building can actually be used to explain some real life stuff that we experience every day, but probably haven't given much thought to. And so that topic is what's called conjugation, all right? And so the tools that we've been building so far, like geometry, like drawing structures, like different ways to represent structures, the condensed, the calculate or skeleton structure, and also hybridization are all going to kind of be wrapped up within this lesson. And so our two goals for today are one, to be able to identify what's called a conjugated system within a molecule, and then also being able to illustrate it using p orbitals, kind of like we did when we were sketching the orbitals while talking about hybridization. And so I'm going to start here. I've got most of the notes kind of typed out just to make it a little easier for us to go through them quickly so you won't have as much writing to do. But again, this sheet is on your Schoology page if you want to print it out and follow along. So where this word conjugation comes from is actually from a Latin word that means to link together. So kind of think about a big chain where all the individual links are connected. And so the idea is, well, we've got to be linking something together. And so what we're linking together are actually going to be the p orbitals within a pi bonding system. Now, if you remember, when we are having a pi bonding system, you have to at least have a double or triple bond. What happens when you have a double or triple bond is you end up with a hybridization of either sp for a triple bond or sp2 for a double bond. And if you remember, let's just pretend we have sp2 hybridization for a second. What that means is you're mixing one s orbital and two p orbitals in order to generate three new hybrid orbitals. But the catch is, what that leaves is one unhybridized p orbital that can then be used to create a pi system. So it's the unhybridized p orbitals that we're really interested in, okay? And when we have pi systems, kind of several in a row, it's going to allow those p orbitals to interact continuously so that the effects are linked together. And so just a couple of illustrations of this on the side here. This first one on top is what's called an isolated pi system. And that's when you just have a double bond by itself. So here, these two carbons, instead of drawing that second line, what they're showing is the interaction between those p orbitals. And the key is for those p orbitals to be able to overlap, they have to be in the same plane. So the p orbital on that first carbon is sticking up and down. The p orbital on that second carbon is also sticking up and down as well. And so that allows them to interact. That creates that double bond pi system. It's isolated because it's just those two adjacent atoms. However, let's take a look at this second molecule that we have here. It's a longer molecule, and it has two double bonds separated by a single bond. Now, if we were to go through and label the hybridization of each of these double bonded carbons, they would each be sp2. That's because they have 3 electron regions. 3 electron regions is a hybridization of sp2. So, if they're all sp2, that means all of these carbons have an unhybridized p orbital that's available for interactions. And that's kind of sketched here to the right. And so those unhybridized p orbitals can all interact kind of along the tops and the bottoms of that molecule. And that's what creates what's called an extended pi system, where you have alternating double bonds, so double bond, single bond, double bond, single bond, double bond, single bond, and each of those carbons are going to have an unhybridized p orbital that can participate in that pi system. And when you have that extended pi system, it's going to lead to some neat chemical properties, some extended reactivity, okay? And so that main thing that we're going to be looking at is, do we have alternating double bonds? Do we have unhybridized p orbitals that are in the same plane? Now, if you happen to have adjacent p orbitals, but they're not in the same plane, they're not going to be able to interact because no overlap is possible. So here this picture is illustrating a p orbital kind of sticking straight up and down, and the other p orbital has kind of been tilted at an angle. So again, in order for this conjugation to work, the p orbitals have to be lined up parallel with each other in order to overlap and interact. Okay. So again, here's the main point. A conjugated system requires that continuous array of p orbitals that will produce this pi bonding overlap along the entire system within the molecule. So if for some reason that system is broken by an atom that does not have a p orbital, or if the p orbital is not in the correct geometry, then you're going to lose the conjugation or linking at that point. And what that continuous overlap of p orbitals throughout the molecule allows is for those pi electrons to be delocalized. Now the word local means that it's close. It stays in one location. Delocalized means spread out. And so what happens is, instead of these pi electrons belonging to a single carbon atom, okay, they can be spread throughout the entire molecule. So that's this idea of delocalization, is that extended pi system allows the electrons to be spread over many of the atoms instead of just localized to the specific atom that it came from. All right, so we're going to walk through just a couple of examples here before we give you some time to practice. So our examples are written mostly in Kekulé form. So we're going to need to remember that the carbons and hydrogens are hidden. So remember, at the end of each point, we do have a carbon, and we assume that there are enough hydrogens to give those carbons a total of 4 bonds. So in this first example, where we just have a double bond, we can assume that each carbon needs 2 more hydrogens in order to arrive at a total of 4 bonds. Next, we want to assign hybridization. This carbon on the left has 3 regions, 1, 2, 3. So its hybridization will be Sp2. The same will be true for the carbon on the right. Now, with Sp2 hybridization, what that means is that you have an unhybridized p orbital available on each of those carbons. So if I draw in a p orbital, okay, what those p orbitals do is they provide that pi interaction to generate a double bond. The hydrogens, of course, having 1 electron, don't have any p orbitals to participate, so the pi interaction here is just limited between those 2 carbons. So this is what we call an isolated system. It's just occurring between 2 adjacent atoms. However, if we go to the next molecule, here we see that pattern of alternating double and single bonds. So let's do some interpretation right quick. Remember that each of these points represents a carbon. So this molecule has 4 carbons. Now let's remind ourselves of where the hydrogens come into play. The carbon on the left already has 2 bonds, so we need 2 more hydrogens to complete the 4 bond pattern. The second carbon already has 3 bonds, so it only needs 1 more hydrogen. Third carbon, same thing, 1 more hydrogen remaining, and then the carbon on the end requires 2 more to complete the 4 bond pattern. Now let's go through and identify the hybridization that we see. This carbon on the left has a hybridization of sp2. It has 3 different regions. The carbon next to it also has a hybridization of sp2. It likewise has 1, 2, 3 regions. And that same can be applied to the other 2 carbons within the molecule. So carbons that are double bonded typically have sp2 hybridization. Now again, remember, what this means is that each of those sp2 carbons have an unhybridized p orbital. Okay, they have an unhybridized p orbital, and the hybridized orbitals are the ones that are creating the single bonds. We're just kind of keeping them as single bonds today, just since we're focusing on the pi system. So I'm going to draw in the other hydrogens, just to kind of illustrate that there. There we go. And so the p orbitals, we've got kind of 2 sets of interactions. The p orbitals, the half of the p orbitals that's on top, those are interacting by kind of sharing or spreading around their electrons. And then the second half of the p orbitals on bottom are sharing or delocalizing their electrons as well. And so what we see is this pi interaction is not isolated to just 2 adjacent carbons. Instead, it extends further within the molecule. And so this is what we call an extended or a conjugated system. I'll put extended in parentheses. All right. So now let's look at this third example. Now this one looks somewhat similar to the one we just did before. However, instead of having alternating double and single bonds, we have a double bond, then a single bond, then another single bond, and then finally back to a double bond. So let's remind ourselves of the carbons right quick, and that middle carbon is drawn in for a very specific reason we'll soon see. So each of these points represents a carbon, and they've kind of helped us out by drawing in the hydrogens already. So now let's go through and assign hybridization to each carbon. This carbon on the left is sp2 hybridized. The carbon second to left is sp2 as well. Now, let's take a look at this middle carbon. If you notice, this middle carbon, he is bonded to 2 hydrogens, and he is single bonded to 2 other carbons. So what this means, if he has 4 bonds, that is 4 electron regions, which means that his hybridization is sp3. Now remember, with sp3 hybridization, both the s and all 3 of the p orbitals are mixed. So that creates 4 new hybrid orbitals, and we don't have any unhybridized p orbitals left over. So those 4 hybrid orbitals are used to make its 4 single or sigma bonds. If we keep going in the molecule, we would find that the other 2 carbons on the right are also sp2 hybridized as well. So let's see if we draw this out, what happens. So let's make sure we get our 5 carbons, and we're kind of drawing to reflect geometry. Everything is connected by at least a single bond. Got 2 hydrogens here. Got 2 hydrogens on my carbons on the end. Let's get all those in there. All right. So now let's draw in the p orbitals on the atoms that have them. So this carbon is sp2. It would have an unhybridized p orbital. The middle carbon is sp3. So again, it does not have an unhybridized p orbital available. But my carbons on the right, being sp2, would. So if I kind of shade in the tops of my p orbitals here, the tops of my p orbitals could interact, and the bottoms of the p orbitals could interact kind of on the underside of the molecule. And so what happens though, because we have that sp3 carbon right there in the center, it has broken what could have been a conjugated system into 2 isolated systems. So we have an isolated pi system on the left that's just between 2 adjacent carbons, and an isolated pi system on the right that is again just between two carbons. So an sp3 carbon can kind of get in the way and prevent conjugation throughout the whole molecule, while instead creating separate isolated sections. Now right quick, just to kind of throw something in that's kind of interesting, this is just to kind of expose you to this. You won't actually be asked to apply it at the moment. But sometimes atoms with lone pairs can kind of convert to an sp2 hybridization in order to create a conjugated system within a molecule. Conjugation is really favorable. It's a good thing. It benefits molecules when it happens. And so let's say you have something like this NH2 here. Now normally, if we redrew this, you've got your nitrogen, it's got a lone pair, it's got two hydrogens, it's got a double bond to this carbon over here and a carbon here. And if we drew in our carbons and hydrogens, here is what we would have. Okay, so this carbon and this carbon are both going to be sp2 hybridized, being attached to that double bond. Let me see if I can write that more neatly. Sorry, colored pencil didn't work well. So these are both sp2 hybridized, which means they would both have an unhybridized p orbital, being able to participate in pi interactions. Now, this nitrogen on top we would typically consider to be sp3 hybridized. That's because it has 4 electron regions. So typically we would consider that to not have an available p orbital. But what happens is that nitrogen with the lone pair kind of converts to an sp2 hybridization. And what it does is it takes that lone pair and puts it within the pi system. And so now what that does is creates that extended conjugated system within the molecule where you're able to connect 3 different atoms, the 2 carbons and the nitrogen, instead of just an isolated system with those carbons. So that's just kind of neat that that atoms with lone pairs can adjust to create a favorable conjugated system. Okay. Oops, don't want to move that. All right. So let me scroll down here and get off this text box, and we'll show you what you're going to do to practice. So what we've got here is a little practice chart with a few different molecules, and you're going to practice labeling or drawing out the p orbitals within the pi system, and then telling me if it's conjugated, that's kind of extended, isolated, or what's called cumulated, and we'll kind of come back to that one at the end. So let's work through the first one together just so I can show you how I'd like you to go about it. So propene is the name of this particular structure, and they've given us the Kekulé structure to kind of practice thinking about those hidden carbons and hydrogens. So again, every carbon is a point, or every point is a carbon. And it's helpful, just as you're still learning, to go ahead and fill in enough hydrogens to get those carbons up to 4 bonds apiece. So let's get that all filled in here. Then what I would recommend is going through and assigning a hybridization to each of the carbons. These carbons involved in the double bond are sp2 hybridized, while this carbon on the end, who's involved in a single bond with the 3 hydrogens, is sp3 hybridized. So then what we're going to do is kind of re-sketch the molecule. Fill in our hydrogens. And we want to connect everything with at least one single bond. We're not going to draw out the hybridized orbitals for the single bonds just so we can focus in on those pi orbitals. So if something is sp2 hybridized, it's going to have a p orbital that is unhybridized and therefore available for pi interactions. And so let's get in the habit of kind of shading the top half of our p orbitals and leaving the bottom half unshaded. And what we're going to draw, if we have 2 p orbitals next to each other that are in the same plane, we're going to kind of illustrate their interactions. Do that with just some dashed lines. That'll work. And so then, once we illustrate the pi system, we say, okay, is it conjugated, which means extended throughout a good portion of the molecule? Is it isolated to just two adjacent carbons? Or cumulated is where we have two pi systems kind of side by side. And that example again we'll talk about at the end. So mainly the ones I want you to focus on are conjugated or isolated. So here, because that pi interaction only occurs between two adjacent carbons, that's going to create what's called an isolated system. So we have isolated conjugation. All right, so this one right quick, the second one I want y'all to skip for now, and we're going to come back to it after y'all have had a little bit of time to practice. But let me go ahead and help y'all with one more. Maybe let's do one of the rings. How about this 1,3-cyclohexadiene? And then I'll let y'all pause the video and finish the others. So again, let's kind of go through and draw in those hidden carbons and hydrogens. These are carbons that are just connected in a cyclical ring structure. And again, don't forget about those hidden hydrogens. Every carbon needs enough hydrogens to complete its 4 bonding pattern. All right, there we go. So once you get your carbons and hydrogens drawn in, go ahead and assign hybridization. So we'll start with this first carbon on the right that has 4 electron regions. That means that 4 electron regions corresponds with Sp2 hybridization. That will also be the same case for this carbon below it. Now, the other carbons within the molecule participate in at least one double bond. That's going to give each of them only 3 electron regions. As a result, the remainder of our carbons are going to be Sp2 hybridized. Okay. So now when we go to sketch, we're going to keep in mind that the Sp2 carbons will have unhybridized p orbitals, while the Sp3 carbons will not. So let's go ahead and draw in our p orbitals. Okay, shade the tops, leave the bottoms unshaded, and then we can fill in our hydrogens. Okay, so we do have p orbitals that can interact, that are all in the same plane, running up and down. And so we'll kind of draw in those interactions with some little dotted lines here. And so because those interactions carry over more than just 2 carbons, we are going to have what's called a conjugated system. That's where we're linking together the p orbitals in that pi system throughout the molecule. So that would be an example of a conjugated system. And to show you this kind of illustrated just a little more nicely, let me scroll down here. So here's the one that we just did, 1,3-cyclohexadiene. So it's a flat ring structure here. Here are those double bonded carbons around the side. And so those 4 carbons with their double bond, they're able to participate in that conjugated system, while these 2 Sp3 carbons are not. All right, so what I'd like you to do is to go through and finish the remaining 4 examples. So take some time, kind of work through those. If you have your model kit, I highly recommend kind of building the models as you work. It just really helps get you in that 3D brain. So go ahead and finish those 4 problems just like we did the first 2 examples. Pause the video, and then once you finish, if you'll click the video back on, and we'll go over the answers together, and we'll also talk about that one that we skipped. All right, welcome back. So let's go over those answers for those 4 that you worked right quick. The first one being 1,3-pentadiene. So let me scroll back up here to this guy right here. So here's our 3D model of 1,3-pentadiene. Here are 2 double bonds. The carbons attached to the double bonds are sp2 hybridized, so they all have an unhybridized p orbital that's available to participate in pi interactions. That makes this a conjugated system. So there's your 1,3-pentadiene. Your next one was just a cyclical version of this, which was 1,3-cyclopentadiene. So it's this guy right here. So here again is your 3D structure. So kind of a flat molecule overall with some of the hydrogens on this carbon sticking out to the side. Now this carbon at the top is sp3 hybridized due to its 4 bonding regions. However, those carbons attached to the double bonds are sp2 hybridized and have those available p orbitals to participate in the pi system. So this does create a conjugated system kind of around the back end of the molecule, but it does not involve that tip carbon at the top. All right, now let's tackle the 1,4-cyclohexadiene and then what is called benzene. 1,4-cyclohexadiene. Okay, so here's 1,4-cyclohexadiene. Now, what's interesting about this one is you have a double bond on either side of the molecule, but on both the top tip and the bottom tip, you have an sp3 carbon. So what happens is that creates 2 isolated systems, one on the left between these 2 p orbitals and one on the right between these 2 p orbitals. So those sp3 carbons at the tip break the conjugated system into 2 isolated groups. Now finally, we have benzene, which is a super duper cool molecule. It takes the same kind of 6-sided hexagon as cyclohexadiene, but what's different is that benzene has 3 double bonds instead of just 2. Those 3 double bonds make all of the carbons in a benzene ring sp2 hybridized. So they all have an available p orbital with which to participate in pi interactions. And so what that creates is a conjugated system that extends across the entire ring. So super cool, and that leads to some really neat properties within that molecule. Now the last one that I want to go back and talk about is the one that we skipped, which is called 1,2-propidine. It's also more commonly known as alene. And so on this one, kind of you have an odd keculae structure, and you'll notice that little break in the middle. So there's 1 carbon in the middle and then 2 carbons on the side. And we're going to find that this carbon, the structure is drawn linearly for a reason. So let me pull back up my little thing here. And let's go up to that one. Here it is. So here is 1,2-propidine or alene. So let me turn it on its side right quick. And what you'll notice is that those double bonds create kind of a line throughout the molecule. Now, the end carbons each have 2 hydrogens attached. But let me turn the molecule as if we're looking at it face on. What we see is that 2 of the hydrogens on this carbon on the left are pointing kind of up and down, while the 2 hydrogens on the back carbon are pointing to the sides, one to the left and one to the right. And so what we're going to find is that this creates kind of an interesting system within this molecule. So I'm going to go back where I can write on this right quick and kind of try to illustrate what's happening. So these 2 carbons on the end are going to have the hydrogens attached, but that carbon on the middle does not have any hydrogens because it already has 4 bonds from those 2 double bonds. So if we assign hybridizations, the 2 end carbons are sp2 due to their 3 electron regions. However, the center carbon is actually going to be sp hybridized because it only has 2 electron regions. Now if we remember, in sp hybridization, we're only mixing an s orbital and a p orbital. That leaves 2 p orbitals unhybridized. So this middle carbon is actually going to have 1 p orbital that runs up and down, and it will have a second p orbital that kind of runs in and out of the paper. So imagine that it's kind of sticking out there. Let me redraw that. I always have a hard time drawing the ones that are sticking out of the paper. So we've got one going up and down, and then we've got one kind of coming in and out of the paper at an angle. And so what happens to create this interaction, the one carbon on the right is going to have a kind of sideways p orbital, or his will have to orient sideways. And the other carbon will have to have his p orbital kind of oriented up and down in order to interact. So what we have is kind of two sets of p orbital interactions that are occurring kind of side by side. So we've got this interaction and this interaction. Of course, you've got your single bonds here as well. And so this is what creates what's called a cumulated system, where we have those back-to-back p orbital interactions. There's no alternating double bond, single bond, but everything's just kind of accumulated right there in the middle. And so to kind of show what that looks like here, you've got a little better picture of where you've got one interacting set of p orbitals doing their interaction up and down, and the other set doing it side to side. So it's cumulated there right on that center carbon, since it has two unhybridized p orbitals due to its hybridization. All right, now I've been awfully patient, so let's wrap this up with some application. So where conjugation comes into play is those extended pi systems are oftentimes what lead to color within different foods or fruits, or within different dyes that we use to color our clothing or different things like that. And so what we find is that the longer your conjugated system is, the longer the wavelength of color you will see that's associated with that molecule. So we've got three kind of food-related molecules here. We've got lycopene, and it has 11 conjugated pi bonds that are marked in red for you. Beta-carotene also has 11 conjugated pi bonds, but you'll notice that a few of them are kind of in a ring structure as well. Lutein has 10 conjugated pi bonds. So what we see is those long conjugated systems tend to give us longer wavelengths of color, like red, orange, yellow. And this explains some of the colors that we see in our food. For example, lycopene is the red pigment found in tomatoes. Lutein, a yellow pigment, occurs in egg yolks. And then beta-carotene, an orange pigment, is found in carrots. And so it's these molecules and their structural characteristics that lead to these big macroscopic properties that we can see, such as the color of some of our foods. Oops, and I forgot I had this little illustration here. This is the allene one more time, showing the side-to-side interactions, while also having the top-to-top interactions kind of all accumulated on that middle carbon. So I just forgot I had that more nicely illustrated picture of that. All right. Now, what's interesting is this can conjugation can also explain a lack of color. And so you'll notice this is kind of a molecular structure for natural rubber latex. Okay. And so this molecule has a lot of double bonds. So it's got a lot of p orbitals, a lot of pi bonds. But however, you'll notice that these are not conjugated. All of those pi bonds end up being isolated. And so it doesn't create that conjugated system that can absorb and transmit different wavelengths of light. So that lack of conjugation kind of results in this natural rubber latex being really white and not having a bright color like orange or red or yellow. Now this is also interesting because this kind of applies to stain removal. So if you've ever heard of OxyClean or like some of your stain removers here. Oops, I thought it would just let me click it, but maybe not. Here it goes. I wanted to show you all this right quick. It's got a funny little picture on here. All right, so we've all been at that point where we have maybe eaten something and gotten something on our shirt, and it's especially bad, if the shirt is a light color such as white. And the poor mom of this little boy who is eating a burger and making quite a mess with his ketchup. So it looks pretty difficult to clean. And so you may often hear of people using Clorox bleach to kind of make their whites whiter or to remove stains. Commonly used for things like ketchup or grass stain, things that tend to be pretty brightly colored. And so what bleach, or how it works rather, is it actually kind of unconjugates the molecule. Bleach in particular, its active ingredient is hypochlorite. And so what happens is the stains that tend to have these long conjugated systems react with the hypochlorite, and it turns all of those double bonds into kind of new single bonds to an OH on one side and a chlorine on the other side. And so what happens when those double bonds are destroyed, it undoes the conjugation and it undoes the color. So here's the thing. That stain molecule is still present, you just can't see it. So when you're using bleach on your clothes or towels or whatever, you're not actually removing the stains, you're just removing the color. So the stains are still there, you're just not seeing them at the moment. And so that's why you need other things like detergent to actually take the stain molecules away. But that's how a lot of stain removers work, is by removing the color so that the stain doesn't show up, that bright color on your nice white shirt. So just kind of interesting how some of this works on an everyday practical application. So y'all have been phenomenal hanging with me on this lesson. You'll get to practice this a little bit more in your homework, and then you'll also be doing your first reading from the Napoleon's Buttons book. And Will, my fantastic, wonderful husband, kind of tested that book out for us over the summer. He read the whole thing. I haven't made it through the whole thing yet. But essentially, it is showing how chemical molecules have had an impact on history. And so chemistry doesn't occur in just a bubble. It's around us, every day, impacting our lives, our history, our world. And so you're going to be reading chapter 9, which is on dyes. And so that directly relates to what we've talked about today with conjugation. So I hope you enjoy getting some more applications through that chapter. But thanks so much. I hope you'll have the most wonderful day, and I'll see you next time.